Hello physics students. So in the last video, you learned the physics definitions of the words work and power. And what you saw in that video was that these terms in physics were defined mathematically. In other words, with formulas. Take, for example, the definition for work. Work equals force times distance times cosine of the angle. That means in physics, work is not done unless there's a force over a certain distance. Furthermore, the force and the displacement have to be oriented properly in order for there to be work done. In other words, the angle between the force and the displacement cannot be 90 degrees because the cosine function is 0 for theta equal to 90. This would be the situation where I carry something horizontally with a displacement at a constant velocity. And all I'm doing is I'm supporting it in the upward direction as I'm carrying it horizontally. Yes, there's force. Yes, there's displacement or distance. The angle is 90, makes 0 work. The work can be positive, 0, or negative. It can be positive when the angle is less than 90, like 45, 30, or even 0 degrees. And in general, what that means is that you're pushing the object in the same direction as it's moving. That generates positive work. If, however, the angle is greater than 90 degrees, like for example 180, then the work is negative. That's the case where an object is moving in the forward direction, but you're pulling it backwards. Then the work you do is negative. Okay, so that is the definition of work. Today we're going to move on and learn the definition for energy. Okay, and just like work and power, this term energy is something you've used in your everyday life. Oh, I have a lot of energy today. That was a very energetic piece of music. So again, you have to use the physics definition of energy in physics class. So to help us understand what the definition of energy is in physics, I have here a little demonstration. I've got some batteries. Batteries generate electricity. Most people would recognize that that has energy. Okay? Now, what I could do with that that energy in those batteries is a whole host of things. I could run an electric motor, or I could turn on a light like this. So you see now that light is producing light energy, which is another kind of energy, and it's supplied by the batteries. But what exactly is battery energy? Well, you probably learned this earlier in the science class, but a battery has a positive and a negative terminal. And we'll be learning more about this later in the year. But the key thing that's happening is there's a chemical reaction in here. There are reactants that turn into products. One end of the battery, the reactants are pushing electrons out of the battery. So you might be guessing what that is in terms of the definitions we've already learned, where it pushes the electrons out. The other end of the battery, the positive side, pulls the electrons in, pushing and pulling over a distance. What does that sound like? You should be thinking work, and you are correct. Energy is the ability to do work or the transfer of work. And that also is what's happening in the light bulb. These electrons are being dragged over these atoms in a sense. Just like when we drag a block over a surface and there's friction and it makes heat, these electrons are dragging over these atoms and making heat, and then that metal is glowing red hot or even white hot, and that's the light. So again, a transfer of work, the ability to do work. But let's suppose the batteries go dead, and so now they won't turn the light on anymore. Well, I could get new batteries if I want to light the light, but suppose I don't have any. What I could do is get a generator. This is called a hand crank generator for obvious reasons, because you crank it with your hand. I could hook this to the light and turn it on instead by turning the handle. And once again, we could see a transfer of work. I'm going to push a force times a distance in the same direction. I push this to the right and the handle moves to the right. And then I wrap that around in a circle. Okay, so I do that and I'm putting in work in the handle and the light is turning on. So transfer of work, that's energy, okay? What if I didn't want to turn the handle of the generator myself? Well, I could get a motor to do that, like a gas-powered motor, but let's suppose I don't have that. What I could do is I could modify this generator like I've done over here. I basically cut little holes in the plastic and I wrapped a thread around the axle of the generator in there. And you can't see the thread probably because it's, a little tiny thread, and also it's black, so it doesn't really show up that well. But what I'm going to do is I'm going to take and hook to this thread these masses. And then as they fall, they'll turn the axle, okay? And what I want you to do, and let me take the handle off to get it out of the way. What I want you to do is to watch as the masses descend that the light comes on. In other words, falling masses can also do work or energy. So here we go again. Let's see, a little awkward here. All right, let's try holding it like this. All right, watch this light bulb turn on as the masses fall. Ready? Go. All right, you saw that light come on, energy. What did it come from? The masses going down. And so these masses, for a moment, did the same thing the battery did. The batteries have energy, those masses had energy. So in a sense, these masses are just like a rechargeable battery. How rechargeable? Well, if I wanted to, I could take this down, wind the thread again, and wind it up, and then recharge these batteries by lifting them up. Now they're charged batteries again, able to release the work or the energy when they fall. Now the batteries are dead. I charge them up, recharge them. Batteries go dead, lighting the light. No different than your cell phone. At the end of the day, it's dead. It will not turn on, so you plug it in overnight. The battery fills up and charges with this thing called energy, and then throughout the day it depletes. Plug it back in, charge it back up, depletes. Okay, so masses, you may never have realized that masses are like batteries. But how exactly am I charging these batteries up? Think about it. To lift this, I've got to put a force. It's not going to go up by itself, so I'm going to put a force, and then that force is going to move over a distance. Force, distance, I put work in to charge the battery. So now this is stored work. I hook it on, and then the mass as it descends, it pulls on the thread of force times the distance, it gives back the work. Battery dead, I put work in, it gives it back. Put work in, gives it back. So that's a new kind of energy other than battery energy, and we need a name for it. So in physics, for obvious reasons, probably you'll see, we call it gravitational potential energy. And that's the topic for today. So what I'm going to do is reconfigure the camera. We're going to summarize what we saw here, as well as learn an equation for the amount of energy you get when you charge something up by lifting it. All right, okay, so here we are. The topic for today, gravitational potential energy. The symbol we use in the Regents for this kind of energy is PE for potential energy, and then a little subscript for G, gravitational. There's another kind of potential energy we're going to learn in the next video, so that's why we need a little subscript there. So this is just a diagram of what we saw, kind of summarizing the idea of what gravitational potential energy is. We've got a generator up high, string wrapped around an axle, and a mass up high. When this goes down, it releases light energy through the generator. But the key idea here is when I lift this to recharge this battery, I put in a force times distance in the same direction. I put in positive work, put work in to lift the mass. Then when I let this go, the mass returns force times distance the mass returns the work as it descends. Now, that's the concept. The equation, the amount of potential energy or work stored in a mass is PEG equals mgh. The mass must be in kilograms, g is 9.8 in meters per second squared, and the height must be in meters. Now, interesting, work, right? That's what potential energy is, the transfer of work. We could see work in this formula. What's mg? mg is the force of gravity or the weight of something in newtons. Force times distance, work, okay? That's what PEG is. Don't forget that. I'm going to emphasize that a lot. All these energies are work, and I'll explain why I emphasize that later in another video. All right, so let's move on. Oh, let me create a pause if you need a moment to catch up. Okay, moving on. So there are concepts embedded in this formula. How mass affects potential energy, how height affects potential energy. Kind of common sense, when I lift this up, the higher I lift it, the more energy, the more light's going to come out. But also the more mass I put here, it's going to come and make the light even brighter. So that's more energy also, more mass and more height in that formula. But more specific than that, it tells you the exact dependence of mass and height. For example, if I double the mass that I lift up, I'm going to double the PEG, as we could see here. Doubling this will double the answer over here. Let's suppose hypothetically I triple the height. So I take that same 1 kilogram mass, and instead of raising it up like this, I go 3 times as high. More energy. How much more? Well, if you triple the height, you're going to triple this side, you're going to triple the energy. Okay? What about if you do 2 things? Double the mass and triple the height. You look at this formula, double, triple together is 6 times as much potential energy. All right, so time for an example. And this example is going to illustrate another important thing about this potential energy formula. What I have, I'm going to determine the change in potential energy to lift a 6 kilogram mass from a basement to an attic. Okay? And so here's a little diagram of a house. This is the ground level, okay? The basement and the attic. So maybe your parents are asking you to, move some boxes out of the basement, which is too moldy, and they want to store the things in the attic. So you're going to lift this up. What's the change in potential energy? Now, notice there's a lot of space over here. I want to make sure that when you draw this, leave space over here, because we're going to solve this problem twice with 2 different perspectives to make a point about gravitational potential energy. Now, if this is the ground level, we say it's H equals 0. Makes sense. That means if I go down underground 2 meters to go into the basement, I've got to call that negative 2 meters. I'm going below H equals 0, underground. This being 4 meters above ground level, the attic, I'm going to call that H is now positive 4, okay? And so what I need to do is calculate to determine the change, the initial potential energy and the final potential energy. So let's do that. All right. So if you need a moment to catch up, let me pause the video to give you a chance to catch up. Okay, let's continue on. Let's calculate the initial potential energy and the final potential energy. So this is what I'm going to call method 1. So the first thing, the PE initial. mgh is the formula. So I've got 6 kilograms, 9.8 is G, and the height was negative 2 meters underground. If I multiply that all out, I get negative 117.6. And the answer is joules, like work and energy, both measured in joules. That's the initial potential energy when it's underground, negative potential energy. What's the final potential energy? Again, mgh. So I take my 6 kilograms, 9.8 is G, and now we're at a height of +4 when we're in the attic. If you multiply that out, you get 235.2 joules. And now, the change in potential energy. Well, the change in anything, just like when we did change in velocity for acceleration, you do the final minus the initial. In other words, the final is positive 235.2 minus the initial of negative 117.6. Now, punch that on a calculator and you should get positive 352.8. Do that on a test, and you'll get the question correct. Now, I'm going to resolve this, but let me create a little pause in case you need a moment to catch up. Okay, so here's another way I could solve this. Let's suppose instead I decide that I want to call the basement height equals 0. And you say, what do you mean? How can you do that? The ground's 0. Well, just bear with me. Let's see what happens if we do that. That makes the attic a total of 6 meters above 0 meters. So now the attic is no longer +4, it's got to be +6. And let's resolve with that new way of looking at the same problem. I don't even need to calculate PE initial. I'm starting at 0. 0 height, 0 energy. So why bother calculating it? So if I want to calculate the PEG at the top, I'll now use mgh again. And 6 kilograms (9.8), and the new way of looking at it is it's 6 meters above the h equals 0. And when you punch that on your calculator, you're going to get 352.8. And if I ask what's the change when you go from 0 to 352.8, it's just 352.8. Oops, delta. So you get the same answer if you call the starting bottom point 0 and reconfigure the final point based on that new h equals 0. So, let me, in case you need, before I move on, let me give you a chance to catch up if you need it. Okay, so 2 different ways you get the same answer. Which is easier? Obviously this one. So that's the interesting thing about potential energy gravity. You could make h equals 0 anywhere you want. But once you decide that that point is h equals 0, you got to keep it h equals 0 for the rest of the analysis. You can't say, well, before it was convenient to call it 0 here, now I'm going to call it 0 because I like it better over here later in the problem. No, h equals 0 here, it stays there for the rest of your analysis. So let me summarize. So you can set h equals 0 arbitrary, can set anywhere it is convenient, but after that must stay consistent for the rest of the analysis. Let me give you a chance to copy that down. Okay, so that's gravitational potential energy. By the way, it is on the reference table, and because of this idea that h can be 0 anywhere, on the reference table the formula is listed as such. It's right here in the back. If you go down near the bottom, you see that they don't give you PEG, they give you what delta PE is, and it's mg delta H. That's to indicate that it's the change in altitude that matters. In other words, you can set h equals 0 at the bottom of your motion and do the analysis that way. But I always prefer to write the potential energy without the delta symbols. It just looks simpler and nicer. All right, so let me remind you, what is energy? Do you remember? It's the ability to do work or the transfer of work. These batteries push electrons around a circuit with a force times distance. So it's transfer of work to the electrons. Or I could crank with a generator, force times distance, and I generate energy out of this generator. Or we can lift a mass up, force times distance, I put energy in, I put work in, and then later I let it go, oops, I let it go, and I get back that work, that force times distance. So potential energy gravitation is energy or work that's stored by lifting an object. All right, I hope you enjoyed the video. I'll see you in the next physics video.